All right. Good morning. Welcome to my stream. What did we do last time? Yesterday's stream, let's switch over here. Yep, there we go. Okay, so what we did yesterday was worked on the text editor. And we got up to, we finished part 3 and we were going to start part 4, or we got up to part 3 and we're done with part 3. Tomorrow we'll work on part 4, but today we're going to work on the interpreter again. So hopefully that'll be fun. Let's see. Right, so where do we leave things off? We cleaned out this. Git status is clean, right? Yeah. Okay, we're good. Let's take a look here and just see where we are with this. That's the bytecode. That RLTK it will come back to someday. As soon as they update the tutorial, we can make that go away. Mizzard. Oh, right, yes, right. That's right. Mizzard was helping me with the macro. That I got to get done. Supercuber. Supercuber wrote rlocks. That's right. And we never... Oh. It got interpreter version and a bytecode version here. Neat. Right, and using workspaces. And code instruction. Why is that separate? Just curious. Okay. Why is that a separate crate? I don't know. Programmer, hello. Good to see you. Right, we can keep that. We're going to keep that, and this is on the other screen. So, okay, so let's dig into. Oh, let's just hit refresh on this guy. Just see. No, still no end game. All right, we'll get there eventually. So for garbage collection, we don't have a lot to do in this code because Rust manages all the garbage for us. So there's 3 ways to manage memory, right? One is the C way, where you're responsible for the allocations and the frees. The other way is the Java way, which is it keeps track of what's allocated and what's not allocated, and eventually will free up every so often during a major GC or a minor GC. JavaScript has those concepts of a major and minor GC. I don't know how Java works. And then you have the Rust way of doing it, which keeps very careful track of who owns what and what memory belongs to whom, and when it goes out of scope, it gets freed automatically right then and there, and you don't have to worry about calling free. To allocate memory, right, we have RC, which is not in this file. Maybe in the compiler, we'll have plenty of RCs, yep. So when we see RC new, we're actually allocating a reference counter to point to the compile result that resides somewhere in the heap. And the reference counter is responsible for freeing the memory when the reference count drops to 0. We also have box. I don't think I use box anywhere. No. But box allocates something that can be referenced by one thing and then gets dropped when that reference goes away. So let's see. So garbage collection seems to indicate this. The bytecode interpreter is going to be doing it the Java way with a periodic garbage collector. So let's just skim through this, and then we can get to classes and instances. We say LOX is a high-level language because it frees programmers from worrying about details irrelevant to the program they're solving. The user becomes an executive, giving the machine abstract goals and letting the lowly computer figure out how to get there. Dynamic memory allocation is a perfect candidate for automation. It's necessary for a working program, tedious to do by hand, and yet still error-prone. The inevitable mistakes can be catastrophic, leading to crashes, memory corruption, or security violations. It's the kind of risky yet boring work that machines excel at over humans. That's why LOX is a managed language, which means the language implementation manages memory allocation and freeing on the user's behalf. When a user performs an operation that requires some dynamic memory, the VM automatically allocates it. The programmer never worries about deallocating anything. The machine ensures any memory the program is using sticks around as long as it's needed. LOX provides the illusion that the computer has an infinite amount of memory. Users can allocate and allocate and allocate and never once think about where all those bytes are coming from. Of course, computers don't yet have infinite memory, so the way managed languages maintain this illusion is by going behind the programmer's back and reclaiming memory that the program no longer needs. The component that does this is called a garbage collector. Recycling would be a better metaphor for this. GC doesn't throw away the memory, it reclaims it to be used for new data, but managed languages are older than Earth Day, so inventors went with the analogy they knew. Okay. How does a VM tell what memory is not needed? And this is all about reachability now. VMs cannot travel into the future. Instead, language makes a conservative approximation. It considers a piece of memory to still be used if it could possibly be read in the future. Conservative GC is a special kind of collector that considers any piece of memory to be a pointer to the value that looks like it could be an address. Oh, this is in contrast to a precise GC, which is what we'll implement. It knows exactly which words in memory are pointers and which store other kinds of values like numbers or strings. Okay. Couldn't any bit of memory be potentially read? Actually, no. At least not in a memory safe language like LOX. Here's an example. var a equals first value, a equals updated, garbage collection here, print a. Say we run the GC after the assignment has completed on the second line. The string first value is still sitting in memory. There's no way for a user's program to ever get to it. Once a got reassigned, the program lost any reference to that string. We can safely free it. The value is reachable if there's some way for the user program to reference it. Otherwise, like the string first value here, it is unreachable. So what happens if I do that? Cargo run. Right? If I say var a equals first value and a equals updated, print a. So it's still getting global a. And what's happening is a is just global and it's referring to this constant value. Then we created a new script which created an update for a constant value. And then we printed out the global variable that was there. So what happens in our VM? We have these globals that are part of the hash map. So what happened was when we set the global, there's define global, there's get global from our print statement, here's set global. We overwrote. This is in the Rust version, obviously. We overwrote the value we were pointing to with the new value. That was right here. And I can just print that overwrote. And we should be able to see that come out. Yep, right there. So we hit that line of code. But it means that whatever value was there is no longer being referenced, right? And it was just a regular value. So Rust needs to see that, right? Or the get mute code, which is over here, which is over here, which we don't have, I guess. I tried to jump to the source of this, but I guess it doesn't exist. It had to have freed whatever it was pointing to before assigning this. Or not, it doesn't have to be that in that order, but basically anything that this was pointing to now has to get freed right then and there by Rust. Many values can be directly accessed by the VM. Take a look at this. Pause that program right after the two strings have been concatenated before the print statement has been executed. The VM can reach string by looking through the global variable table and finding the entry for global. It can find another by walking the value stack and hitting a slot for the local variable local. It can even find the concatenated string another, since that temporary value is also sitting on the VM stack at the point when we pause our program. Right, but that's just on the stack, right? Because we have that the add binary op. So we push that's this thing here. We push this onto the stack. So it's in the Rust version, it's referenced on the stack by the VM stack here. All these values are called roots. A root is any object that the VM can reach directly without going through a reference in some other object. Most roots are global variables or on the stack, but as we'll see, there are a couple other places VM stores references to objects it can find. Other values can be found by going through a reference inside another value. Fields on instances of classes are the most obvious case. We don't have those yet. We'll get there soon, though. Even without those, our VM still has indirect references. So consider this. Say we pause the program on the marked line and run the garbage collector. When the collector is done, the program resumes and will call to closure, which will print data. So the collector needs to not free that string. But here's what the stack looks like when we pause the program. It has the script, it has a closure, and that's it. The data string is inside the closure. Right here. It's been captured by the closure. So we go through the up value 0. It's got the location been closed over, and then it has the data inside the closure. This gives us an inductive definition of reachability. All roots are reachable. Any object referred to from reachable object itself is itself reachable. So we can start with the roots, and I guess this is the root for this, right? Does that make sense? There's the script, and then there's the root of the closure, which you should be able to walk. And then starting with the roots, traverse all references to find a full set of reachable objects and free all objects not in the set. Right, so that saves you having to reference count every object, because that would be the other option, right? Because that's what we're doing in Rust, is having a reference count. So every time we clone a reference count, it just increments a value that's hidden from us somewhere. And then when that drops to 0, it gets freed immediately, rather than doing the garbage collection step. Mark sweep garbage collection. First managed language was Lisp. Second high-level language to be invented right after Fortran. John McCarthy considered using manual memory management or reference counting, but eventually settled on and coined garbage collection. Once the program was out of memory, it would go back and find unused storage it could reclaim. John McCarthy's History of Lisp, he notes, once we decided on garbage collection, its actual implementation could be postponed because only toy examples were being done. Our choice to procrastinate adding a GC to CLOCs follows in the footsteps of giants. Okay. He designed the very first simplest garbage collection algorithm called mark and sweep, or just mark sweep. So we start with the roots. Yeah, I'm skimming this. I'm not going to read the whole thing. So we start with the roots, and then each time we visit an object, we mark it in some way. Once the mark phase completes, every reachable object on the heap has been marked, so any unmarked object is unreachable. That means you have to keep track of all the objects somehow, right? So that's what we're going to implement. All right. Whenever we decide it's time to reclaim some bytes, we'll trace everything and mark all the reachable objects, free what didn't get marked, and then resume the user's program. Of course, we'll end up adding a bunch of helper functions too. Oh, the entire chapter is implementing this one function, collect garbage. All right, so how does this work? We'll add an optional stress test. GC runs as often as it possibly can. It's obviously horrendous for performance, but it's great for flushing out memory management bugs that occur only when the GC is triggered at just the right moment. If every moment triggers a GC, you're likely to find those bugs. Okay, that makes sense. Whenever we call reallocate, we force a collection to run. All right, this might be done better with a environment variable, so you don't have to keep recompiling to test your code. More sophisticated collectors run on a separate thread, right? Often a function called boundaries or when a backward jump occurs. Collecting right before allocation is the classic way to wire GC into a VM. You're already calling into the memory manager, so it's an easy place to hook in the code. Also, allocation is the only time where you really need to free some memory up so you can reuse it. If you don't use allocation to trigger a GC, you have to make sure every possible place in the code where you can loop and allocate memory also has a way to trigger the collector. Otherwise, the VM can get into a starved state where it needs more memory but never collects any. Yeah, so this is kind of an important point, right? But if you're running it in a separate thread, then the thread can just wake up periodically, I guess. And then debug logging, or we can watch the GC in action. Okay, so marking the roots. How do we do that? Right, so each entry on the stack gets marked. That makes sense. That gets starting. That's our starting position. And then we just have a mark object function. So obviously we're adding this marked flag to every object. That's right, they get chained together. Every new object begins life unmarked because we haven't determined if it's reachable or not. And then I guess we mark whenever we have the debugger on, we say which one we're marking. Okay. And then we mark the globals table. All right, yeah, so those are the two things. And then do we have to worry about call frames? That's the only other thing that's in the VM. Mark value. What's the difference between mark object and mark value? Is that a different? Because this mark object is setting the marked flag to true. Mark value. Okay, so values get marked separately. Okay, the garbage collector doesn't need to worry about them at all. So the first thing to do is ensure the value is actually heap object. If so, the real work. Okay. Okay, so marked value is like the interface, and then we just have to mark the object if it's an object. Okay, I see it. We walk the entry array. For each one, we mark its value. We also mark key strings for each entry, since garbage collection manages those strings too. Right. Those cover the roots we typically think of, the values that are obviously reachable because they're stored in variables the user's program can see, but the VM has a few of its own hidey holes where it squirrels away references to values that it directly accesses. Most function call state lives in the value stack, but the VM maintains a separate stack of call frames. Yep, that's what I knew we had to get there eventually, right? Each call frame contains a pointer to the closure being called. The VM uses those pointers to access constants and up values, so those closures need to be kept around too. What I'm storing, though, on the call frame, that's interesting, is a just pointer into the VM stack and slots. I forget. Slots, I think, is just how many slots to go back. So we've already essentially marked everything on there. So I'm a little... It's a good thing we don't have to do it, because I'm a little puzzled as to how this is different. I guess because this is a pointer to the closure. But the closure is on the stack already, is what I'm saying. Alright. The open up value list is another set of values the VM can directly reach. So we have to mark those. But aren't those also on the stack? Remember that a collection can begin during any allocation. These allocations don't just happen when the user's program is running. The compiler itself periodically grabs memory from the heap for literals and constant table. Right. Mark compiler roots. So the compiler has... Oh, it has the function and then the enclosing, right? So while the compiler is running, I think we call this compile result. right? We have the chunk that we're doing, we have the enclosing that we're referring to. There's the current function, which is just a string, name of a string. Fortunately, the compiler doesn't have too many values it hangs on to. All right, so then the next step is tracing object references. I slotted this chapter into the book right here, specifically because we now have closures, which give us interesting objects for the garbage collector to process. So once we've marked everything, I guess, okay, so now it's time to implement that traversal. So we're going to traverse over all the objects that are remaining. We can go breadth first, depth first, or in some other order. Since we just need to find a set of all reachable objects, the order we visit them mostly doesn't matter. Some garbage collectors move objects in the order they are visited, so traversal order determines which objects end up adjacent in memory. That impacts performance because CPU uses locality to determine which memory to preload into the caches. Yeah. So it would be probably better to do it in address order, right? Collector wanders through the graph of objects. We need to make sure it doesn't lose track of where it is or get stuck going in circles. This is particularly a concern for advanced implementations like incremental GCs that interleave marking with running pieces of the user's program. The collector needs to be able to pause and then pick up where it left off later. So the VM hackers came up with a tricolor abstraction and then used white, gray, and black, none of which have colors. At the beginning of garbage collection, every object is white. The color means we have not reached or processed the object. Gray means during marking, when we first reach the object, we darken it to gray. So we know the object itself is reachable, but we haven't looked at what it's pointing to. And then black means we've looked at everything that object's pointing to. So the marking process now looks like start off everything with white, find all the roots and mark them gray, and then repeat as long as there are still gray objects. To pick a gray object, turn any white object mentions to gray, and then mark the original gray object black. Yeah, I know, I follow all of this. I don't need the diagram. It makes sense, right? You start at the root, you mark everything it can reach gray, then you go to the first one and see if there's anything it references, mark those gray, and then mark the node black, and then go to the next gray. Mark those as gray, and that becomes black, and then so on and so on. At the end, you're left with a sea of reached black objects sprinkled with islands of white objects that can be swept up and freed. Note that at every step of this process, no black node ever points to a white node. This property is called the tricolor invariant. The traversal process maintains this invariance to ensure that no reachable object is ever collected. Okay, so VM gray capacity is less than gray count. Oh, this is just extending, okay, an array. So we have this array of gray stacks, which just every time we mark something as gray, we put it onto a stack to process later. That makes sense. And this is just a pointer to the object that we're marking as gray. And yeah, so inside the VM, we would maintain that for the garbage collector. Okay. To be more robust, we can allocate a rainy day fund block of memory when we start the VM. If the gray stack allocation fails, we free the rainy day block and try again. It may give us enough wiggle room on the heap to create the gray stack, finish the GC, and free up more memory. Yeah, so yeah, if you can't allocate space to mark and free, then you can't, you don't know what's freeable at that point. All right, then we have trace references, which goes through the gray stack and blackens the object, which just goes through every object it references. Well, it will, and mark those. So natives and strings, we don't have to worry about, I guess. up values have to be marked, or the closed values in them have to be marked. Okay, and then functions. Yeah, function chunk constants. Right, so all the constants need to be marked, and the name of the function needs to be marked. Okay. But they don't refer to anything themselves. Yeah, this just loops over each value and marks each value. Okay. And then last object is a closure. But again, doesn't the... Oh, that's right, the closure itself. Let's take a look. Closure itself has up values in an array that got closed over. Okay, so that's why those need to be checked, and we actually have those in a reference count as well. All right, and then sweeping unused objects. After you've marked everything black, so at this point things are either black or white. There should be nothing gray left. And then you walk your way through each object in the entire objects array. If it's marked, oh, then we just move it down the linked list. Okay, that makes sense. Otherwise, it's unreachable, so we pull it out and this way, and then relink the other ones. Oh, I see. Or relink it to the beginning if needed, and then free it. Okay. I know that's kind of a lot of code and pointer shenanigans, but there isn't much to it once you work your way through it, right? So if we're going to free this one, we have to get this next pointer to point over here so that we can free this. And the way to get this next pointer to point over here is to take this pointer and copy it over here. And if previous happens, if previous is not null, then we link it to the object, its next pointer to the object. Otherwise, it's the beginning of the list, and so it just gets object. Pretty straightforward. Oh, and we have to set mark to false. All right. After a sweep completes on the remaining objects are the live black ones with their mark bit set. That's correct. But when the next collection cycle starts, we need every object to be white. So whenever we reach a black object, we go ahead and clear the bit now in anticipation of the next run. We're almost done collecting. It's one remaining corner of the VM that has some usual requirements about memory. Recall that when we added strings to clocks, we made the VM intern them all. That means the VM has a hash table containing a pointer to every single string in the heap. That was one of the things I left out, was string interning. And I thought I put a little comment in maybe. Twitch DD says, why not flip-flop the colors instead of having to add an additional overhead of clearing the color to white? Yeah, that's not a bad idea, right? Rather than doing it for every object, just say, okay, next time we're going to start with white. And we're going to start with everything is black now, and then we're going to flip it to white. Yeah, that's a good idea. So we did, and I must have taken it. Let me just take out the I there. Yeah, I must have taken it out because there was no reason to do it, really. What file would it be in though? Token? I thought it would have been in value, but maybe not. When we create a new string, we're not doing any string interning here. And basically, that means is if you have two things. If I say cargo run var a equals foo, var b equals foo. What the code should do is say, oh, look at that, a and b both contain the constant value foo. I'm only going to store foo once and then have a and b both point to that. But in this version, I don't have that. What? Where would it have been? Maybe in the compiler? Or maybe... No, the scanner wouldn't do it. There's no parser here, right? Just the compiler would be the only place that we could do that. Right, keep track of all the... keep track of all the strings as we parse them, and then just determine if we need to... Let's see, fn string. How do we do that? Yeah, I just say value stir string. I don't do anything fancy. So it's possible that the string table has to be dealt with as well. So I guess we do that here. And then when to collect. Okay, so that's an interesting question. Is when does this need to be done? We have a fully functioning mark sweep garbage collector now. When the stress testing flag is enabled, it gets called all the time. And with logging enabled too, we can watch it do its thing and see it's indeed reclaiming memory. But when the stress testing flag is off, it never runs at all. So it's time to decide when the collector should be invoked during normal program execution. As far as I can tell, this question is poorly answered by the literature. When garbage collectors were first invented, computers had a tiny fixed amount of memory. Many of the early GC papers assumed you set aside a few thousand words of memory, in other words, most of it, and invoked the collector whenever you ran out. Simple. Modern machines have gigs of physical RAM hidden behind the operating system's even larger virtual memory abstraction, which is shared among a slew of other programs all fighting for their chunk of memory. The operating system will let your program request as much as it wants and then page in and out from the disk when the physical memory gets full. You never really run out of memory, you just get slower and slower. So it no longer makes sense to wait until you have to run the GC, so we need a more suitable timing strategy, or subtle timing strategy. To reason about this more precisely, it's time to introduce two fundamental numbers used when measuring a memory manager's performance: throughput and latency. Every managed language pays a performance price compared to explicit user author deallocation. Time spent actually freeing memory is the same, but the GC spends cycles figuring out which memory to free. That time is not spent running the user's code and doing useful work. In our implementation, that's entirely of the mark phase. The goal of a sophisticated garbage collector is to minimize that overhead. So throughput is the total fraction of time spent running user code versus doing garbage collection work. Say you run a CLOC program for 10 seconds and it spends a second of that until you collect garbage. So the throughput is 90%. Up until this chapter, CLOCs had no GC at all and thus 100% throughput. They still put the allocated object in the linked list, so there's some tiny overhead for setting those pointers, right? And latency is the longest continuous chunk of time where the user's program is completely paused while the garbage collection happens. To measure how chunky the collector is. Oops. All right. I see. If you like analogy, imagine your program as a bakery selling fresh baked bread. Throughput is the total number of warm, crusty baguettes you can serve to customers in a single day. Latency how long the unluckiest customer has to wait in line before they get served. Okay. Our collector is a stop-the-world GC, which means the user's program is paused until the entire garbage collection process is completed. If we wait a long time before we run the collector, then a large number of dead objects will accumulate. That leads to a very long pause while the collector runs and thus high latency. But every time the collector runs, it spends some time visiting live objects. If you run the GC really frequently, then the user's program doesn't have enough time to even generate new garbage for the VM to collect. We want something in the middle, so not something that takes forever and not something that runs too frequently. We want our GC to run frequently enough to minimize latency, but infrequently enough to maintain decent throughput. So how do we find that balance? I'll be honest with you, this is not my area of expertise. this is something you can build an entire career on. Garbage collecting. Interesting. I read a lot of literature and all the answers I got were vague. The strategy I ended up picking is common, pretty simple, and good enough for most uses. The idea is that the collector frequently automatically adjusts based on the live size of the heap. We track the total number of bytes of managed memory that the VM has collected. When it goes above some threshold, we trigger a GC. After that, we note how many bytes of memory remain, how many were not freed. Then we adjust the threshold to some value larger than that. So as the amount of live memory increases, we collect less frequently in order to avoid sacrificing throughput by retraversing the growing pile of live objects. Alright, I mean that sounds like a reasonable approach. As the amount of live memory goes down, we collect more frequently, so we don't lose too much latency by waiting too long. Okay. The challenge with learning garbage collectors is that it's very hard to discover the best practices in an isolated lab environment. You don't see how a collector actually performs unless you run it on the kind of large, messy real-world programs it's actually intended for. It's like tuning a rally car. You need to take it out on the course. Yeah. I wonder if they have like garbage collector test suites, right? So, right. So every time we allocate some bytes, we keep track of it. If it hits the threshold, then we call collect garbage. Now finally, our garbage collector actually does something when the user runs a program without our hidden diagnostic field enabled. The sweep phase frees objects by calling reallocate, which lowers the value of bytes allocated, so after the collection completes, we know how many live bytes remain. The threshold is a multiple of heap size. This way, as the amount of memory the program uses grows, the threshold moves farther out to limit the total time spent retraversing a larger live set. I mean, I'm not sure. I'm trying to think about how would an incremental, we talked about incremental garbage collector, how would that work? Because you have to traverse everything in order to know what's referenced. So how can you traverse just a little bit and then free stuff up? Okay, garbage collection bugs. In theory, we're all done now. We have a GC, it kicks in periodically, collects what it can, and then leaves the rest. If this were a typical textbook, we could wipe the dust from our hand. So I'm still processing in the back of my head. How could you do an incremental GC? Could you separate memory into chunks that you allocate from, and then, and then just scan those chunks? But how could you ensure that one data in one chunk doesn't reference data in another chunk? Yeah, I don't know. I don't know how you'd make it incremental. If this were a typical textbook, we would wipe the dust from our hands and bask in the soft glow of the flawless marble edifice we've created. But I aim to teach you not just the theory of programming languages, but sometimes painful reality. I'm going to roll over a rotten log and show you the nasty bugs that live under it. Garbage collector bugs really are some of the grossest invertebrates out there. Collector's job is to free dead objects and preserve live ones. Mistakes are easy to make in both directions. If the VM fails to free objects that aren't needed, it slowly leaks memory. If it frees an object that's in use, the user's program can access invalid memory. These failures often don't immediately cause a crash, which makes it hard for us to trace backward in time to find the bug. This is made harder by the fact that we don't know when the collector will run. Any call that eventually allocates some memory is a place in the VM where collection could happen. It's like musical chairs. At any point, the GC might stop the music. Every single heap allocated object we want to keep needs to find a chair quickly, get marked as root or stored in reference in some other object before the sweep freeze comes to kick it out of the game. A GC can't find addresses in the C stack, but many can. Most well-known list of varieties, the Bohm Demers Advisor Garbage Collector. This is a mark sweep algorithm, provides incremental and generational collection under operating systems which provide the right kind of virtual memory support. SunOS, IRIX, OS X, Linux, and Windows. Allows finalization code to be invoked when an object is collected and can take advantage of type information to locate pointers if such information is provided, but is usually used without such information. Garbage collector works with most unmodified C programs simply by replacing malloc with gcmalloc calls, and replacing realloc with gcrealloc, and removing free calls. Interesting. Wow. Interesting. It doesn't say how it works in here, but okay. The shortest path to fame in CS is the last name that's alphabetically early, so it shows up first in sorted lists of names. Okay. Many precise GCs walk the C stack too, even those have to be careful about pointers to live objects that exist only in CPU registers. Yeah. Okay. How is it possible for the VM to use an object later, one that the GC itself doesn't see? How can the VM find it? The most common answer is through a pointer stored in some local variable in the C stack. The GC walks the VM's value and call frame stacks, but the C stack is hidden to it, right? In previous chapters, we wrote seemingly pointless code that pushed an object onto the VM's value stack, did a little work, and then popped it right off. Most times I said this was for the GC's benefit, and now you see why. The code between pushing and popping potentially allocates memory, and thus can trigger a GC. We had to make sure the object was on the value stack so the collector's mark phase would find it and keep it alive. I wrote the entire CLOX implementation before splitting it into chapters and writing the prose, so I had plenty of time to find all those corners and flesh out most of the bugs. Stress testing code we put in the beginning of this chapter and a pretty good test suite were very helpful. Where's that? But I only fixed most of them. I left a couple in because I want to give you a hint of what it's like to encounter these bugs in the wild. If you enable the stress test flag and run some toy-lox programs, you can probably stumble into a few. Give it a try and see if you can fix any yourself. Okay. You're very likely to hit the first bug. The constant table each chunk owns is a dynamic array. When the compiler adds a new constant to the current function's table, that array may need to grow. The constant itself may also be some heap allocated object like a string or nested function. The new object being added to the constant table is passed to add constant. So let's take a look. Let me pull this up again. So where we store the constants is in the chunk itself, right? Okay. Yeah, and that's this value array thing that we don't really need, but we have it in here anyway. Which is just an array. This should have just been a vec of values, but we have it here. All right. So function appends the object to the constant table. If the table doesn't have enough capacity, it needs to grow. Calls reallocate. This in turn triggers a GC, which fails to mark the new constant object and thus sweeps it right before we have a chance to add it to the table. Crash. Fix, as you've seen in other places, is to push the constant onto the stack temporarily. Does chunk have a push pop? Oh, I gotta go to chunk. Yeah. Okay, so we're pushing it onto the code. Oh, that's pushing a byte. That's it. So where is this pushing? Where is it pushing it to? Oh, I guess we're pushing it onto the VM stack. Okay, that's awkward, right? Because the VM could be using the stack. Well, I guess we're single threaded, right? So we're either compiling or we're running. So if we're compiling, we can kind of cheat and use the VM stack for a bit. I mean, the other option would be for the garbage collector to use a chunk stack as its root objects as well. Here's another similar one. All strings are interned in CLOX, so whenever we create a new string, we also add it to the intern table. Since the string is brand new, it isn't reachable anywhere, and resizing the string pool can trigger an allocation. So we need to push the string before setting it onto the table, putting it onto the table. And the last example, over the interpreter, op-add can be used to concatenate. Right. So we never have to worry about any of this also. I mean, Rust handles all of this for us. Okay. So that's the whole chapter on garbage collectors. Skimmed through. That took an hour. Epic Blog says, haven't been able to watch your stream in a while. How's the interpreter crafting going? I'm about to start crafting classes and instances now. Perfect timing. Yeah, so we just went through garbage collecting, and we don't have to do any of that in the LOX interpreter we're writing, because Rust handles that for us. Just like the whole chapter on. Let me scan back here and see. Yeah, there's a whole chapter on hash tables, which we got to skip. I think I skimmed it, right? Because we don't need to worry about hash tables, because we get one of those in the standard library. I guess if we wrote this with no standard, right? Then we would have to write our own garbage collector. No, not garbage collector. Our own hash table. Oh wait, but speaking of which, doesn't Rust doesn't have a defined memory module, but I thought there was a way you could write your own. Rust. I guess memory management implementation. Own it. Welcome to Rust Memory, Stack and Heap, Rust Memory, Memory Management in Rust. There's got to be simple slab-based malloc implementation of Rust. Can be used standalone in order to provide the necessary interface to Rust's liballoc library. Okay. Epic says, yeah, you can set a custom global allocator. There's a bunch of stuff here. Rust, custom global memory management. Let's go with that. In a given program, a standard library has one global allocator used by Box and Vec, for example. CUI-lib and static libs are guaranteed to use system by default. So we could have written our own, right? And then, but I guess that still doesn't handle the whole. We wouldn't need to do garbage collecting because Rust would still tell us when to dealloc. Twitch asks, are you planning on writing your own language after you read crafting interpreters, or are you just going the book for fun? I am going the book for learning. I've written languages before, but very simple toy ones. But maybe it would be fun to write, can I take what I've learned and write a basic interpreter, for example? That might be fun. Eric says, I wrote a no standard Windows application which sets up a global allocator to use raw Win32 heap management functions. A 6K Rust Hello World executable. Wow. Yeah, and what's the normal size? Let's find out. 461K to write hello world to the world. So 6K is pretty good. But that's because the static library is linked in here, right? So so let's do classes and instances. I have an hour left. Let's make this happen. Okay, so the last area left to implement in CLOX is object-oriented programming. Let me just take a quick look back here. Where was this? Already lost it. Yeah, table of contents. Here we go. So we're on 27. So we're going to still have methods and initializers, superclasses, and then I'm not sure what optimization is going to be about. I don't know if that means looking at the generated bytecode and trying to clean that up, or doing something else. We'll find out. We'll get there. All right, OOP is a bundle of intertwined features: classes, instances, fields, methods, initializers, and inheritance. Using relatively high-level Java, we packed all that into 2 chapters. Now we're coding in C, which feels like building a model of the Eiffel Tower out of toothpicks. We'll devote 3 chapters to covering the same territory. This makes for a leisurely stroll through the implementation. After strenuous chapters like closures and the garbage collector, you've earned a rest. If only this would be a rest, right? I don't know. We had tremendous difficulty getting it to work in the tree walk interpreter. So let's find out. I'm kind of leery about getting this chapter started. So self. I've never heard of the language called self. Self has objects but no classes. CLOS has methods but doesn't attach them to specific classes. C++ initially had no runtime polymorphism. Huh. And Python has multiple inheritance and Java does not. Ruby attaches methods to classes, but you can also define methods on a single object. Yeah, JavaScript is kind of a mishmash. It's a prototype language, not an OOP language. Okay. In class-based object-oriented language, everything begins with classes. They define what sorts of objects exist in the program and are the factories used to produce new instances. Going bottom up, we'll start with their runtime representation and then hook that into the language. By this point, we're well acquainted with the process for adding a new object type to the VM. We'll start with a struct. So in our code, we have this value thing. This is where we've been adding all the things. So what does class take? We can just have a class, probably an RC of some kind, right? What's in a class? Just a string? I'm going to guess that this is going to grow. We're going to need more things than just a string. So I'm going to say RC class here. And then import class. And then create a class. And pub struct class name string, and then go into main and then add it here, mod class. All right. And then in order to get this to compile, we're going to have to implement all these things. Or do we? Like this one is none, this one's false, and then clone, we'll need to clone it. Right? We definitely need to clone it. We definitely need to print it. How do we print a class? Let's scan forward here. Here's allocation. Here's freeing. We have to mark it for the garbage collector. Here's printing. Okay. Class simply says its own name. So we can just say class. Oops. Class. You have to write it with a K. And then class.name. Or should I implement display for class and just do this? Yeah, let's do that. Oops. Source class. Oops. Oh, I haven't saved it yet. Okay, let's do that. That's gonna fail. Here's class. Oops. There we go. And then we can just say impl display for class. I forget what the signature is. Let's go take a look at value. Okay, and then it's just going to be right bang f this self name, no semicolon. That's that. Okay. Oh, it doesn't have debug. Okay. That's right. I got to fix my file searcher so I don't have to do this. And this needs to be debug. Okay. So now we have classes. Get status. Class base type. That way I have class in my Git files. Oops. Okay, so what are we going to do with this class? Class declarations. Runtime representation in hand. We're ready to add support for the classes to the language. Next we'll move to the parser. Okay. Which is in compiler. Declaration. All right, so if, I guess we can just copy paste class, put the else there, self class declaration. Right, that's all this is. And then we have this class declaration add after function. Okay. All right, so this looks pretty short. There must be more to this than this, right? Oh, I see. We're doing a left brace, right brace, and I guess the code in between is going to be a block or something when we get there. Let's find out. Self consume, token type, identifier, let name constant is equal to self identifier constant. Oh, how do we do this? Right, because we have issues with borrowing. Let's find out. Where else do we do this? Not there. Here's identifier constant. Oh yeah, these lines. Okay, let's grab these and go back to where we were and paste those there. So this is called name constant. Oh no, this is just constant here, and then let name constant equals this, right? Okay. That's there. And now declare variable. We emit some bytes. Opcode class. Oh, we're going to have to add that, right? Name constant. And then self-define variable. Name constant. There we go. And then we're going to consume the left and right brackets. So this would be left brace and right brace, and expect this before class body. I don't have to double it for the closing one, right? After class body. Immediately after the class keyword is a class's name. We take that identifier and add it to the surrounding function's constant table as a string. As you just saw, printing a class shows its name, so the compiler needs to stuff the name string somewhere in that runtime, somewhere that the runtime can find. The constant table is the way to do that. Class's name is also used to bind the class object to the variable of the same name. So we declare a variable with that identifier right after consuming its token. All right, so we're creating the identifier constant here, and then we declare and define the variable here. We could have made class declarations be expressions instead of statements. They're essentially a literal that produces a value after all. Then users would have to explicitly bind the class to a variable themselves, like var pi equals class something. Sort of like lambda functions, but for classes. But since we generally want classes to be named anyway, it makes sense to treat them as declarations. Okay, next we made a new instruction to actually create the class object at runtime. Yeah, so this is going to fail to compile until we add this new class opcode. That instruction takes the constant table index of the class's name as an operand. After that, but before compiling the body of the class, we define a variable for the class's name. Declaring the variable adds it to the scope, but recall from a previous chapter we can't use the variable until it's defined. For classes, we define the variable before the body. That way users can refer to the containing class inside the body of its own methods. That's useful for things like factory methods that produce new instances of the class. Finally, we compile the body. We don't have methods yet, so right now it's simply an empty pair of braces. Locks doesn't require fields to be declared in a class, so we're done with the body and the parser for now. And the compiler is emitting a new instruction. Let's fix that. So it's just class, and then we have to add it down here. Code class. Add it to the disassembler. So opcode class becomes self constant instruction op class offset. And we don't have to pass in chunk to any of these functions because we have chunk as part of self. So that saves us an extra parameter. For such a large seeming feature, the interpreter support is minimal. We push a new class object onto the stack. Okay. Opcode class. We need to read the string. So how did we do that before? That would be what? A get global? Or get local? No, this would be global, right? So it would be just like get global. Copy these guys, put those here. Can we do this? Can we say let class string equals this, then return s, else panic. Unable to get class name from table. Can I do that? And then we can just say self push. It's a new class, value class. I have to write class new now with the string. Oop. I forgot the read constant. I took the wrong thing out, didn't I? Okay. Yep, so in class, oh, I don't have class here. Why did I put all these together? Class, star. And S is not found in the scope. Oh, class string. And we don't have new, so let's go over here and write a new. Impl class. Pubfun new. S string. Returning self. And then just self name. Boom. Failure. Expected RC. RC new. Okay. We load the string for the class's name from the constant table and pass that to new class. That creates a new class object with a given name. We push that onto the stack and we're good. If the class is bound to a global variable, then the compiler's call to define variable will emit code to store that object from the stack into the global variable table. Otherwise, it's right where it needs to be on the stack for a new local variable. There you have it. Our VM supports classes now. You can run this. Unfortunately, printing is about all you can do with classes, so next is making them more useful. Local classes, classes declared inside the body of a function or block, are an unusual concept. Many languages don't allow them at all, but since LOX is dynamically typed scripting language, it treats the top level of a program and the bodies of functions in the blocks uniformly. Classes are just another kind of declaration, and since you can declare variables and functions inside blocks, you can declare classes in there too. Alright, so cargo run. Let's see if I can define a class. I'm not going to type brioche because I can't type that, but I can say class foo. There's our new class opcode. It defined a global called foo. So foo, print foo, and it will print foo. So it was able to print the class name. Okay, so that's 27.2, which is called class declarations. Let's check out with Clippy. Oh, right, there was something I did yesterday with the kilo thing. Git hooks. What was it called? Pre-commit? Yeah. Which allows me to do a cargo format, cargo Clippy, and I don't have tests. But let me copy this over. So now, before I can check in, it's going to run all of those things. Git add source, git commit -m section 27.2 class declarations. It just takes a little longer. There are code style issues. Really? Okay. Why didn't we ever get that before? There. And then we ran all 0 tests, and they all passed. See, this would be good to have from the beginning, because then I can write tests right from the beginning, which would be good to do. All right. Runtime representation in hand. Oh, we did that. Instances of classes. There we go. Classes serve 2 main purposes in a language. They are how you create new instances. Sometimes this involves a new keyword. Other times it's a method call in the class object, but you usually mention the class by name somehow to get the new instance. And they contain methods. These define how all instances of the class behave. We won't get to methods until the next chapter. So for now, we'll only worry about the first part. Before the classes can create instances, we need a representation for them. All right, so now we have an instance. I'm going to have a class reference. Source instance. Let's just source class. Let's do that and just get this instance. Because I'm going to need debug, display, and formatter. So just copy those over. Then we're going to have this table. The table is just a hash map. And it's going to be the same hash map that we had in our globals. Right? Inside VM, we have this. So that means we're going to need this guy. Probably not entry, just hash map. And it's called fields. And instead of a name, it's a class, and it's going to be an RC to a class, which means use create class star. And then the new is going to require a class. So we're going to say class is RC clone class, and then fields is hash map new, like that. And display, I'm going to change this to instance. And then this class changes to instance. And then what does this print out? We'll find out in a minute, I'm sure. So we have a class, a reference to a class, and the fields as a hash map. Instances know their class. Each instance has a pointer to the class that it is an instance of. We won't use this much in this chapter, but it will become critical when we add methods. Being able to freely add fields to an object at runtime is a big practical difference between most dynamic and static languages. Statically typed languages usually require fields to be explicitly declared. This way, the compiler knows exactly what fields each instance has. You can use that to determine the precise amount of memory needed for each instance and the offset in that memory where each field can be found. In locks and other dynamic languages, accessing a field is usually a hash table lookup, constant time, but still pretty heavyweight. In a language like C++, accessing a field is as fast as offsetting a pointer by an integer constant. More important to this chapter is how instances store their state. Locks lets users freely add fields to an instance at runtime. This means we need a storage mechanism that can grow. We could use a dynamic array, but we also want to look up fields by name as quickly as possible. There's a data structure that's just perfect for quickly accessing a set of values by name, and even more conveniently, we've already implemented it. Each instance stores its fields using a hash table. So we just have to include the hash table. Okay, so now we're at the point where we can go over to our value and add instances. Let me save this first. We have to figure out how we're writing it out. Let me scan it forward real quick and just look to see how we're printing it. Here it is in print object. So we're just going to say class name instance. Self.class. All right, so this will call the display on class, and then we just put the word instance after it. Okay, so that should work. Let's add instance here. And then we're gonna have to figure out partial order. We're gonna ignore, leave that as none. Partial equality, ooh, we probably want that. And we probably want it for classes as well. Let's do that. Class, and then instance. There, now it grows. I'm going to be silly here, aren't I? And put them in length order. Oh, I got number up here. There. Yeah, it looks nicer. Okay. And then, do we need to do clone? We do need to do clone. Okay, I'm not going to put those in any order. And the display for value is just going to be the same thing as this. And I'll have it called the instance display. All right, that works. And then check. It does not check. Could not find instance. Oh, I have to add it to main. RC is missing. What else? Value is missing. RC, and class. Oh, class, there. Okay. All right, 2 warnings. Oh, we're not using fields yet. Okay, we will. Let's get there. All right. Right, so we were talking about adding the table stuff. So this is actually something we get for free from Rust. We get the hash map. We don't have to worry about that. New struct gets a new object type. I want to slow down a bit here because locks' language notation of type and the VM implementation notation of type brush against each other in ways that can be confusing. Inside the C code that makes locks, there are a number of different types of obj string, obj closure, etc. Each has its own internal representation and semantics. In the locks language, users can define their own classes, say cake and pie, and then create instances of those classes. From the user's perspective, an instance of cake is a different type of object than an instance of pie. But from the VM's perspective, every class the user defines is simply another value of type object class. Likewise, each instance in the user's program, no matter what class it's an instance of, is object instance. That one VM object type covers instances of all classes. And two worlds mapped to each other is something like this. Got it? Okay, back to the implementation. We also get our usual macros. Okay, so, right, I get all that. I don't know how that's going to clash with this stuff. We do know for, object equality, we're just comparing to see if the pointers are pointing to the same object. That's creating a new instance of a class. Oh, a new instance of an instance. Yeah, so we actually did all that, right? Which I don't have here. Yeah, so this is just setting up the class and creating a new table for the fields, a new hash map for the fields. The setter end of an instance's lifespan, it gets freed. Again, we don't have to worry about that. Speaking of the garbage collector, it needs support for tracing through instances. We don't explicitly free the entries in the table because there may be other references to those objects. Uh-oh, that means I can't do this, right? This has to be an RC to a value. Otherwise, we're going to end up cloning into the fields. Is that true? I mean, I imagine, so let's say we had a new piece of locks code, xlocks. And we had a class foo, which that we defined. And then say, var a equals foo. Is that how we create a new instance? I've forgotten already. Oh, we don't know. We haven't gotten the syntax down yet. Okay, let's say it's like this. And I say a dot x equals 1, right? That's going to store 1 in a field in the hash map of the instance of a. The name is going to be x and the value is going to be 1. If I said, var b equals bar, and then say a dot bar equals b, is that going to refer to the var b? So if I said, okay, let's change this to 12. So if I modify, say b equals b plus 1, will that change bar, a dot bar? It shouldn't, right? Because this should just copy the value over. So and I don't want to just change this blindly to RC, because then everything's going to have to get RC'd, right? Because if I look at the VM, our globals are not RC'd. The values on the stack are inside a ref cell, so that would imply that this would need RC ref cell. I'm going to leave it like this for now, and then we might have to refactor. Okay. If the instance is live, we need to keep its class around. Also, we need to keep every object referenced by the instances field, right? Okay. The real fun happens over the interpreter. Right, so instance prints its name followed by instance. The instance part is mainly so that classes and instances don't print the same. Most object-oriented languages let class define some sort of toString method that lets the class specify how its instances are converted to a string and printed. If LOX was less of a toy language, I would want to support that too. Real fun happens over the interpreter. LOX has no special new keyword. The way to create an instance of a class is to invoke the class itself as if it were a function. Right. Runtime already supports function calls, and it checks the type of the object being called to make sure the user doesn't try to invoke a number or other invalid type. We extend that runtime checking with a new case, so in call value. Here's call value. Right now we can either call a closure or a native function. So we're saying now we can call a class value class. Right, so now we have the RC of the class. VM stack top of negative arg count minus 1 is equal to object val new instance class. Oh, stack top. Right, we actually had to go through that process here. So let's do that. I was saying, why are we indexing negative values? But we're not. We're going to the top of the stack and indexing backwards from there. So that's the equivalent of doing right, VM dot stack of stack top minus arg count minus 1 is equal to, we're going to basically overwrite it with this value instance rc new instance new class. No problem. And then return true. And of course that doesn't work. Not found in the scope. Oh wait, it's self stack, not VM stack. And instance is not found in the scope. Okay. Will we finally get this on multiple lines now? Instance. Oh, okay. Okay, it doesn't like this. Expected RC. Oh, right, the stack is RC ref cell value. Okay. RC new ref cell new. Wow, that's complicated. RC new ref cell new value instance RC new instance new class. All right, well, we've created an instance. If the value is being called, the object results when evaluating the expression to the left of the operand, opening parentheses, is a class, then we treat it as a constructor call. We create a new instance of the called class and store the result on the stack. We're one step farther. Now we can define classes and create instances of them. All right, let's find out. Hard to run. We're still not using fields. That's okay. Class foo. Print foo. Foo instance. Look at that. It created the foo instance on the stack. Nicely done. Okay. So that's 27.3. And that is called instances of classes. Git status, git add source, git commit, -m, section 27.3, instances of classes. And of course we're going Clippy. Aha! Oh, right. We're going to have to, okay. In order for Clippy to be happy, oh, we can do no check, right? No verify. There. Just skip all of that. All right, that's just for now. We're going to fix it in the next section here. Get and set expressions. Our object representation for instances can already store state. Let's see if I can get through. Ooh, is that the last bit of this chapter? Oh, I don't know. I don't know if I have time. We'll find out. We'll see how far we get, and then we'll leave things hanging for tomorrow. So all that remains is exposing that functionality to the users. Fields are accessed and modified using get and set expressions. Not one to break with tradition, Locks uses the classic dot syntax. Declare.filling equals space between. The period full stop for my English friends works sort of like an infix operator. There's an expression to the left that is evaluated first and produces an instance. I say sort of because the right-hand side after the dot is not an expression, but a single identifier whose semantics are handled by the get or set expression itself. It's really closer to a postfix expression. That's right, we had a thing where you actually, there's a whole series of something dot something dot something dot something, and then that turns into a call, which then results in that being the field. Since there is a preceding operand, we hook this into the parse table as an infix expression. So is it in compiler? No. Yes, compiler. Here we go. So we're going to modify token dot, which I don't think we have set yet. No. So rules, token type dot as usize. And this is going to be, I guess we'll just set the whole thing. Parse rule. It's going to be prefix none. Infix is going to be sum compiler dot. And then a precedence is precedence call. And that's going to be that. And we just need to add dot now. Right. That's the only error. So add after call. fn call. Okay, so as in other languages, the dot operator binds tightly with precedence as high as the parentheses in a function call. After the parser consumes the dot token, it dispatches to a new parse function. So fn call, which is going to dot, which is going to dog. Mut self, going to ignore can assign. Oh, we do use it. Okay, good. This is the first time in a while we've used can assign. Okay. Self consume. Token type identifier. Correct. Property name after dot. Let name is equal to self identifier constant. Oh, right. We have to go through the little dance here. I guess we can shadow it. Right? We can do that, and then we can say if can assign and self is match token type equals assign. There. Yeah, I changed it because we have equal and equals. So assign and equals is a little bit better. Self expression. Self emit bytes. Opcode set property. That's a new code. Opcode. To name. Else. Self emit bytes. Opcode. Get property name. And that's that. The parser expects to find a property name immediately after the dot. We load that token's lexeme into the constant table as a string so the name is available at runtime. The compiler uses property instead of field here. Remember, locks also lets you use dot syntax to access a method without calling it. Property is the general term we use to refer to any named entity you can access on an instance. Fields are the subset of properties that are backed by the instance's state. Okay, so we have two new expression forms, getters and setters, that this one function handles. If we see an equal sign after the field name, it must be a set expression that is assigning to a field, but we don't always allow an equal sign after the field to be compiled. Consider this. This is syntactically invalid according to LOX's grammar, which means our LOX implementation is obligated to detect and report the error. If dot silently parse the equals 3 part, we would incorrectly interpret the code as if the user had written a equals open paren b.c equals 3. The problem is that the equal side of the set expression has a much lower precedence than the dot part. The parser may call dot in a context that has too high precedence to permit the setter to appear. To avoid incorrectly allowing that, we parse and compile the equals part only when can-assign is true. If an equals token appears when can-assign is false, dot leaves it alone and returns. In that case, the compiler will eventually unwind up to parse precedence, which stops at the unexpected equal, still sitting as the next token, and reports an error. If we find an equal in a context where it is allowed, then we compile the expression that follows. After that, we emit a new opset property instruction. That takes a single operand for the index of the property name in the constant table. If we didn't compile a set expression, we assume it's a getter and emit a get property instruction, which also takes an operand for the property name. You can't set a non-field property. So I suppose if the instruction could have been opset field. Oh, like you can't set a function or method. But I thought it looked nicer to be consistent with the get instruction. Okay, so now we have to add these two guys into chunk, and we're going to add them here. Set get property and set property. We'll stick them down here. Okay, and add support for disassembling them. Right here. Op get property. Oops. There we go. Offset, comma, and then this F capital G R capital S. Okay. Interpreting getter and setter expressions. Sliding over to the runtime, which I think if I just try to compile, it should pop us over there. Good. Opcode get property. We'll start with get expressions since those are a little simpler. Okay, so we're going to get the instance and then read a string. Okay, so let's see, what do we do here in terms of, there's let value equals self peak. Okay, so let instance equals self peak. Like that. Oh, and then we're going to have to extract it, right? So if let value instance I is equal to self peak O 0, then we're going to say let name is read string, and we have to do the same thing we did here, right? Maybe I should extract that out. What's the name? Oh, field name. Right? So that pulls the next constant out as a string. Now we have the instance. We're going to create a new value. We're going to pop it and push it. Or we're going to pop the instance and push the value. Because we're getting. Okay, we're doing a get. Oh, okay. So if there isn't, then what happens if this fails? Oh, here it's here, undefined property. Okay, so and we have to do a field. So should we create a function here? We can say self push. Okay, let value equals instance dot get field of name, field name. I'm trying to just work my way through this here. If it's so we're going to say if let some value is equal to that, then we're going to say self push value. Else we're going to say we have a runtime error. Now, how did we handle runtime errors before? Elsewhere, so it's just return runtime. Yeah. So this. And instead of undefined property, we say undefined, sorry, instead of undefined variable, it's undefined property in single quotes. Like that. All right, if this fails, then we want to panic. Expected instance on stack. Just like that. So does that... No. Oh, can't use S. I have to use field name. And doesn't like this. Oh! Can I clone it out of there? Nope. Because I'm cloning the RC. How do I extract the value then from the stack? I must have done it elsewhere. Not there. Peak. Oh, I have to borrow. Right, that pulls it out of the ref cell. No. The expression has type ref value. Okay, now I must have done this elsewhere in this thing. Right, I'm doing a self peak here, self setup value. This borrow is falsy, so I'm calling it directly on the value. I see. I had to do a borrow clone. So I have to clone the instance. And now get field doesn't exist on instance, of course. So let's add that. Not here. Let's put that there, and then pub fun get field self, and this returns an option of value. And we say self fields get name string name. Nope, doesn't like that. Expected enum value found reference to value. I don't want to have to clone it out of the field, because then I'm cloning these values everywhere. Can I do option value like this? And then this has to be cloned onto the stack, right? And then we're missing set property. Okay, so I think that covers get property. Clone galore, yeah, epic. I don't know. I mean, there's at least I'm not cloning it out of here, right? I'm just returning the option of a reference here, and then I'm getting that here. And I do need to clone it onto the stack because we don't want to reference the field in the property from the stack. Okay, so there's the runtime error thing. There's another failure mode to handle, which you probably noticed. The above code assumes the expression to the left of the dot did evaluate to an obj instance, but there's nothing preventing a user from writing this for an obj field. The user's program is wrong, but the VM still has to handle it with some grace. Right now, it will misinterpret the bits of obj string as an obj instance, and I don't know, catch on fire or something. Definitely not graceful. In locks, only instances are allowed to have fields. So that's what we're doing here, right? I'm checking to see if it's an instance, but now instead of panicking, I guess we're going to do this. Runtime error. Return self. Runtime error. Only instances have properties. Okay, that's a little bit better than panicking. We have 5 errors? Oh, darn. Can I borrow self as... Oh, borrow checker. Borrow checker's killing me here. Okay, let me put opcode set property, and I'm gonna have to probably end it here because I'm out of time. Right? If I do this now we have just the borrow checker. So that'll be what we'll do the next stream. Or maybe tomorrow I go, no, I can't. Okay. So tomorrow I'll start the stream off with this, and then we're almost done. We're so close to the end, and then we'll do methods and initializers, or at least get that going. I knew I shouldn't have started this. Dang it. Okay. So we have broken code. I'm going to push up what's there so far, just so it's there, but we have all of this stuff that needs to be dealt with. Oops, VM. Oh, now it's saying it's compiling. What? Cargo clean. And source VM. Yeah, okay, so we're back to this. Okay, so this is what we'll do tomorrow. Thank you everyone for hanging out with me. Thanks Epic for your help and assistance. And I will see you next time where we finish this up and then get back to the editor, which I'm having a lot of fun with, the text editor. All right. Yeah, let's go say hi to Talbot, and that'll be that. All right, take care, everyone, and we'll see you next time.
The next day.
All right, good morning. Welcome back to my stream. I rebooted my system yesterday, so I'm all confused right now. Let's see. Yeah, all my settings are wrong. Okay, good. Good to know. Okay. Yeah, there we go. Okay, so when we left off, so yeah, let me, I at least got into this directory here, git log. What we did last time was we finished section 27.3 and we started 27.4, but we have problems, I think, with the borrow checker. Oops, source VM. And that's where we left things off. If I just do a quick build here, yeah. So we have borrow checking issues that we need to solve, which I don't know, shouldn't be that bad, right? We've done lots of these before. So I think what we're doing here is we're in the get property code. This is the dot, that's the parser. That's the interpreter. Here we are. So this is all we're trying to do, is we're trying to peek at the first thing. We're checking here that it's an instance. We then read the name using these two lines here. And I left this S in there. Right, and we get the field name out. I guess we shouldn't panic, but I don't know. Let's keep going. Then we get the value and try to set the value on the, or we pop it here, right? Where do we pop? We don't have that even. So there should be a pop of the instance, and we throw that away, and then we push the value. Otherwise, we return a runtime error, undefined property field name. So that's where we are now, but of course it doesn't build because we have borrow checking issues, which means we probably have to clone things like always. Let's see, if the thing is not an instance. Oh, there we go. We can do this right up front, right? We can grab let instance is equal to this, and then just move these three lines here. Can we do that? And put a semicolon there, and then these guys get shifted over. Right? And that pulls the instance out, but it might end up causing other issues. Let's find out. We're down to one error. Okay, so that's all we had to do was pull the instance out and clone. We're actually cloning it, which is unfortunate. The question is, are we cloning? Did I add this shift K? Oh yeah, so we're just cloning the reference count. We're not cloning the whole instance. So that's good, right? I added this thing here. You hit capital K and it shows you what the type is. So that's a value. We get the string. That's a string. And now the error is not found in the scope. That's because it's an instance now. And now we still have borrow checking issues. The immutable borrow occurs here. The temporary occurs with access to the immutable borrow. Oh, I see. So yeah, we can't call runtime error here because because this is mutating the value, and this is has a temporary borrow on that value. So we can do this, sum I, else none, and then if instance is none, do that. Does that solve that one? Of course, now we have to instance unwrap. Okay, that's a little awkward, but it does the job, right? We're able to pull the instance out of this thing here, which is what we're trying to do. I don't know if there's an alternate way of doing that. And we could shadow it, right? Let instance equals instance unwrap. There is the or else, right? Arrest, unwrap, or else. Right, and which can run some code, but that just runs some random code. I want to return if it fails, right? And that way we don't have to unwrap down here, but that just, all that does is move the unwrap to a different location. So I don't know if that helps. So I'm going to put that back, take that out. And this is still kind of awkward though. What is this doing? This also has a thing, but oh, right, because we're not. Because we're on an instance, it doesn't matter that this is mutable because this is mutable on self and this is not mutable on self. So why don't we see if we can pull this out like this? Let instance equals this. And then we can let, can we do it this way? Right? And pull all this out. And move this back down to an else clause here. Except I'm missing a thing now. Right, yeah, this thing here. Will that work? Because now that we've cloned the RC, so now we no longer have the reference. Oh, we don't need to unwrap it now. Method not found in value. Value. Oh, right, we got to be doing I again. That worked. Okay, so all we had to do then, so let me just shift K this thing, make sure, yeah, that's a value. It's no longer an RC, which means we're cloning the full instance by doing it this way, rather than cloning the reference counted instance. So if we do this, put this back, it's not like this thing has to be super performant, it just needs to work. Right, so this still builds. Instance is now an option of an RC. And if I look down here, it's an option RC. Can I do Shift K on this unwrap? Yeah, it's not telling me the type though. So let me do this. Let instance equals instance unwrap. If I do that, yes, now instance is an RC. So doing it this way keeps the reference counted variable, whereas doing it the other way actually clones the whole instance. So that's good to learn. Anyway, so that's get property. So that wasn't too bad to clean that up, and then set property. Did I read all this? I think I just came here. So we have the pop and the push, right? And then break. When the interpreter reaches this instruction, the expression to the left of the dot has already been executed, and the resulting instance is on the top of the stack. We read the field name for the constant pool and look it up in the instances field table. The hash table contains the entry with that name. We pop the instance and push the entry's value as the result. Of course, the field might not exist, and LockSweep defined that to be a runtime error, so we add a check for that and abort if it happens. That's there. So that's if the field doesn't exist, and this is if the thing is not an instance. There's another failure mode to handle, which you've probably noticed. The above code assumes the expression to the left of the dot did evaluate to an object instance. Right, that's where we came up with that. Locks could support adding fields to values of other types. It's our language and we can do what we want, but it's likely a bad idea. It significantly complicates the implementation in ways that hurt performance. For example, string interning gets a lot harder. We're not doing string interning, so. Also, it raises gnarly semantic questions about around the equality and identity of values. If I attach a field to number 3, does the result of 1 plus 2 have that field as well? If so, how does the implementation track that? If not, are those two resulting 3s still considered equal? Alright, in locks only instances are allowed to have fields. You can't stuff a field into a string or a number, so we need to check that the value is an instance. If the value on the stack isn't an instance, we report a runtime error and safely exit. Of course, get expressions are not very useful when no instances have any fields. For that, we need setters. Alright, so now we're going to implement the set property. So this is probably going to have similar issues to up here. Although this time we're instances on peak 1 instead of peak 0. Okay. Let instance equals if let value instance of I equals self peak 1 borrow clone. Some I else none. And if I compile that, we get a warning we're not using it, but it's an option RC instance. Okay. And then we're going to set, we have to read the string first and then peek here. Okay, so the way we read strings is this way. Right, now field name should be a string. It is. And then we pop the value. And we're going to pop the instance and then push the value. Okay. So how do we pop? I guess we just say let value equals self pop. Self pop. And this is the instance. I'll put that down here too. And then we're going to self push value. So what type is value? Is RC ref cell value, which is not what we push. I guess we push stack push. Right? And that's that. That's set property. Wow, that was easy. The reason I did stack push instead of just push is because I shouldn't, right? I should. This is a RC ref cell value. Push takes, the type of push is just value, which is why we're cloning it down here. This is just a value. So this isn't going to compile because value is RC ref cell value. I could do a borrow clone. Yeah, that doesn't help. Okay. And that seems to do the trick, except we have issues. We're not using instance. Wait a minute. Oh, because I have to call table set. So what do we have? We have to do this part. I skipped completely over the table set. So right now we have get field, so I guess we have to do instance unwrap set field, field name, and then peak 0. So we can pop it directly. The reason they're doing the peak here is to leave it on the stack for the garbage collector to handle, and then only popping it when they want to get a copy of it. We can pop it first because we're not worried about the garbage collecting. And we can say value borrow clone here. And of course, I don't think set field exists. So let's go to make that pub fun set field. We have to mutate ourselves. Then we have a name. Oh, we need a mutable reference to that. That's probably not going to work. And then I guess value self fields insert name value, right? Oh, I guess this could be one of these fancy ones, right? T is into string, like that. T. We can do that, and then value expected value found reference to a value. Okay, so when we do this, we actually have to clone the value into here. Into. There. That. Yeah, and now cannot borrow data in an RC as mutable. So, what does that mean? That means that this thing has to have interior mutability. This is going to break everything, right? Use standard cell ref cell. Because now we can remove this mute. And we can say fields borrow mute here. And this is borrow get. But I don't think this will return. Let's find out what it returns. Right. So cannot return reference to temporary value, which means we would have to clone it out. After all of that work, to make it nice and clean, we now have to clone out the value. If I say clone though, it's gonna clone what? If I say this, let's do this here. Let v equals this, and then shift K. So that is an option value, and if I say let c equals v.clone, what is that? Option value. Can I do this? Returns a value referencing data owned by the current function. Because it's a reference. And if I pull that out, oh, okay. I thought that cloning this, can I do that? Mismatched types. Oh, yeah, if I do shift K now here, the K is unknown. Why? Option value cannot be dereferenced. Oh, I can do, what's it, asref clone? And that's the option value. And so I can't do that because that's going to still return a temporary. Oh no. Yeah, so what we were returning before was a reference into the instance, and now I want to clone. If I clone this here, if I clone it here, what do I get out of it? I do get an option value, but for some reason it doesn't like that. Oh, because it's temporary. What's the other option to get to switch the to switch it around? Option into result. Now I want to convert option reference to reference option. There's a yeah. Clone is more specific, so cloned is an exact match. Cloned? Oh, there you go. So that's an option value now. Okay. That was what I was missing. All right, so we still have to clone it, which is unfortunate. But this one works, this one works. Then we have to clone this into here. And then going back, we don't have to worry about this being mutable anymore. See, it's an option RC instance. You'd think, if I made this mutable, what would happen? Would this break? Oops. It'll just say it doesn't have to be mutable. If I made set field take a mutable reference to self, that's why I did a ref cell to begin with. Cannot borrow as mutable. What if I let mud instance equals instance unwrap? Can I do that? No. Trait deref mute is required to modify through a dereference, but is not implemented for RC instance. All right. Let's undo those. Undo that. And oops, this is mutable and it doesn't need to be. Okay, so this might do the trick. Let's see if we can set a field. Let's try this. Carter run toast locks. See if this runs or panics. It prints grape. Okay. This is a little more complex than op-get property. When this executes, the top of the stack has the instance whose field is being set, and above that the value to be stored. Like before, we read the instructions operand and find the field name string. Using that, we store the value on the top of the stack into the instance's field table. After that is a little stack juggling. We pop the stored value off, and pop the instance, and finally push the value back on. In other words, we remove the second element from the stack while leaving the top alone. A setter is itself an expression whose result is the assigned value, so we need to leave that value on the stack. Unlike when reading a field, we don't need to worry about the hash table as not containing the field. A setter implicitly creates the field if needed. We do not need to handle the user incorrectly trying to store a field on a value that isn't in an instance. Exactly like with get expressions, we check the value's type. Oh, right. I don't think, am I doing that? I'm not. If instance is none. Return self runtime error. Only instances have fields. There. Cargo check. Okay. And with that, the stateful side of Lox's support for object-oriented programming is in place. Give it a try. Let's try this. Yeah, it printed 3. Okay. It's creating the class, defining a global for it. It creates an instance of pair. It sets first to 1. It sets second to 2. And then it gets first, gets second, sticks them on the stack. There's 1 and 2, and then it adds them together with op add, and there's 3, and then prints it. All right. This doesn't really feel very object-oriented. It's more like a strange dynamically typed variant of C where objects are loose, struct-like bags of data, sort of a dynamic procedural language. But this is a big step in expressiveness. Our locks implementation now lets users freely aggregate data into bigger units. In the next chapter, we will breathe life into those inert blobs. Okay. Speaking of inert blobs, let's git add source, git commit dash. What do we got? 27.4. Get and set expressions. Okay, that went pretty quickly. It only took a half hour to get that done. What if I change that? Let's see. Let's use the same toString business. T into string. And we can just say name.into. Okay, and see if Clippy's happy with that. Nice. Okay. Yeah, at some point I should add some tests, right? Git push. Okay, so now this is up on our... There it is. Get and set expressions. Okay. So with that, I'm going to change gears here, and then update my stream title. And it's stream info. Porting an editor to Rust. That's what I'm going to do now. Let's just grab the. Oops. Sure. Grab that link. Boom. Let's port that text editor. All right. Stream info updated successfully. I'm going to try doing the stream marker here.